this video, we're going to continue our discussion of solving oblique triangles, and we're going to look at a technique we can use to solve triangles that do not have a side angle pair given, or are where we're not in a position to be able to solve for a side angle pair. So we know that using the law of sines is dependent upon us being able to find an angle and the matching opposite side. We take the sine of the angle, divide it by the length of the opposite side, and that creates a ratio that's going to be constant for any pair in the triangle. There are certain situations where we're given information that does define a triangle uniquely, but doesn't allow us to find this side angle pair immediately. So in these situations, we're going to use not the law of sines, but the law of cosines. So the law of cosines max has to be used one time in a problem. So you'll notice when we did the law of sines problems, typically we had to use the law of sines maybe twice. We only have to use the law of cosines one time, just enough to be able to get a side angle pair, and then you can use the law of sines to finish your triangle. You'll find that the law of cosines is a little bit more complicated. The formulas are a little bit more complicated. So ideally, using the law of sines whenever you can is going to be a good option. The law of cosines is going to fill in those gaps where we have gaps though. So the law of cosines states if we have our triangle ABC, and again it's an oblique triangle, don't have a right angle, opposite sides assigned the same way, then one of the three relationships can be used to solve for our relevant unknowns. So the law of cosines essentially has three different forms, and we're relating a side angle pair. So that side angle pair that we relate in each form is going to be what allows us to solve for the side angle pair that we need to use the law of sines. So the first form, a squared, is equal to b squared plus c squared minus 2 times b times c times the cosine of angle A. So notice side A, angle A, those are on the ends, and inside we're using sides B and C. If you were to just rotate all the variables around, you can find all three versions of the law of cosines. If you look at the third version, it looks very similar to the Pythagorean theorem, but it is not the Pythagorean theorem because, again, we're not using anything with a right angle anymore. We're talking about triangles that don't have right angles. So the way we use the law of cosines is going to depend on what we're given and what we're trying to find. So the first case where the law of cosines is going to be necessary is side angle side. So if we're given a combination of this kind of information in that particular order. Now, just like with law of sines, it's not obvious what case you fall under until you label a triangle. So you always want to start by drawing a triangle and labeling it. Identify the side angle pair if you can, find one if you can, and if you can't, you use the law of cosines. So let's look at our first example. So we want to solve the triangle where angle A has a measure of 52 degrees, side B has a length of 22 units, and side C has a length of 35 units. And we want to round the measures of the unknown side and angles to one decimal place. So let's start by labeling our triangle, so A, B, and C. We're given angle A is 52 degrees. We were given that side B is going to be 22 units, and then side C is going to be 35 units. So side, angle, side. Now the only angle we're given is 52 degrees, and notice we don't know what the opposite side length is. And again, if you're tempted to say, well, I'm going to use the Pythagorean theorem, you can't use the Pythagorean theorem. These sides are not contained within a right triangle, so you cannot use the Pythagorean theorem to solve for the third side. So immediately we're at an impasse because the only angle we have is not paired with a known side. So we don't have the information we would need in order to be able to use the law of sines. So since we can't use the law of sines, we're going to use the law of cosines. How do you determine which form to use since there's three different forms? Well, since the only angle we're given is angle A, we're going to have to use the version that contains angle A, in this case the cosine of A. Notice in each of these three formulas, you use the side lengths several times, but you only use one angle. So because we only have one angle given, we're going to have to use the form that references that particular angle. We also have side B and side C, which we'll then be able to plug into the formula, which means our unknown in this case is going to be side A. So once we find side A, we'll then have the side angle pair to use to solve for the rest of the values in the triangle. So I like to start by just writing down the formula, particularly since law of cosines is a little bit more complicated. So we're going to use this form. So a squared is equal to b squared plus c squared minus 2 times b times c times the cosine of angle A. So little a is our unknown. We know side B, we know side C, we know angle A. So we're going to plug those values in. So a squared is equal to b squared, so 22 squared, plus c squared, so 35 squared, minus 2 times b times c times the cosine of angle A, which is 52 degrees. So you'll notice that everything here on the right-hand side, all of that will simplify down to a single constant. So if you're very careful, you can type that whole side in your calculator in one line. You just have to be very careful. So my recommendation is when you write parentheses, use them in your calculator too, just to be safe. So 22 squared plus 35 squared minus 2 times 22 times 35 times the cosine of 52 degrees. And double check that you're in degree mode. If you haven't already done so, make sure you're in degree mode. And so we hit enter, and there we go. Now that's not the value for A, that's the value for A squared. So A squared is equal to approximately 760.8813, we'll round there. Now, as we know, we can keep a running total in the calculator, and so we can write down rounded values just in order to have a way to show work, but as long as we keep that running total in the calculator, there's no need to round until the very end. So when we evaluate A, we're just going to take the square root of what's already in the calculator. So the square root of, copy and paste the answer from the previous line, and then we get our value. So rounded to one decimal place, that's going to be 27.6 units. So side A has a length of approximately 27.6 units. So once we have that value, that is now going to give us our side angle pair. So what do we have left to solve for? Well, we need to solve for angle B, and we need to solve for angle C. So what are we going to do? Well, we're going to use the law of sines. We're going to use the pair we have. Let's go ahead and think about what angle B and angle C would be in relation to everything else that's in the triangle. So the smallest side so far is going to be the side that has a length of 22. That's going to be side B. So that automatically tells us that angle B should be the smallest angle in the triangle. Now side 35, that's the largest side, so that tells us angle C is going to be the largest angle. So a good rule of thumb, particularly when you're doing a law of cosines based problem, is once you start solving for the additional angles, always start with your smallest angle. The reason you want to always start with your smallest angle is because you know automatically it's going to be an acute angle. So any of the issues you run into using the inverse sign, remember when we solve for an angle, sometimes we use the inverse sign. We did that when we used law of sines. Inverse sign kind of is ambiguous in terms of the answer we get from it. We get a first quadrant angle, but there are other angles that meet the requirements for the law of sines that don't actually fit into the inverse sine function. So by specifically solving for the smallest angle first, we guarantee that the angle we find has to be an acute angle, and there's not going to be any ambiguity about which angle is which angle works, which angle doesn't. So because angle B is going to be the smallest one, we're going to solve for that one. So set up your side angle pair. So the sine of 52 degrees divided by the opposite side length, which is 27.6, is equal to the sine of our unknown angle, which is B. So the sine of B divided by the length of side B, which is 22. Okay, so now we want to isolate sine of B. So sine of B is equal to, move your 22 over, 22 times the sine of 52 degrees divided by 27.6. And we know we take the inverse sine in order to solve for the angle. So B is going to be the inverse sine of this expression. So essentially this is the value of sine for our angle. We want to know what is the angle to give us that particular value of sine. Okay, so here's our value for sine. We're plugging that into sine inverse, and we want to determine what angle has that value of sine. So start with everything on the inside. So 22 times the sine of 52 degrees divided by 27.6. Okay, so that's the value for sine. It's less than 1, it's greater than -1, so we know we're going to be able to evaluate the inverse sine without any problems. So plug that into the inverse sine, and we get our angle. So the angle B is going to be approximately 38.9 degrees. Now, how do you know the other angle doesn't work? Because remember, there are two angles that have this as the value for their sine. The other angle would be 180 minus this particular angle measure, minus 38.9. So it would be 141.1 degrees. Well, this angle can't work for two reasons. Number one, if you combined it with the angle that's already in the problem, it's not going to fit. It's going to add up to something that's greater than 180 degrees. But in addition to that, it's also going to violate the rule for side lengths and how they relate to the angles which they're opposite. So we know that side B is going to be the smallest side, so angle B also has to be the smallest angle. If we're saying that angle B is 141.1 degrees, well, that's definitely going to be the largest angle in the triangle, and the largest angle cannot be opposite the smallest side. So 141.1 degrees does not work. You're not going to run into two triangles in these particular kinds of situations. So angle B is going to have to be the angle we get from the inverse sine, so 38.9 degrees. So that leaves us with angle C, which we know has to be the largest angle because it's opposite our largest side. Now we don't have to use law of sines here because now we have two angles. So we can just use that relationship to 180. So 180 minus the 52 degrees we were given minus the 38.9 degrees we just found. So 180 minus 52 minus 38.9, and that's going to give us 89.1 degrees. So angle C has a measure of 89.1 degrees. So this triangle is definitely not to scale, and notice because C is almost 90 degrees, this is almost a right triangle. Almost, but not quite. So we definitely can't use the basic rules of solving a right triangle. We do have to use the law of sines, and in this case, the law of cosines. So this is essentially what it's going to look like when we have an angle given, but the sides we're given don't allow us to immediately find that angle and side pair. So there's another possibility that we could run into where we're given information about a triangle, but we're definitely not given a side angle pair. And that situation is going to be when we're given all three sides. So every situation we've looked at so far, we've been given at least one angle to start with. It's also possible that we could be given all of the side lengths. Well, if we're given all of the side lengths and we don't have any angle to start with, that presents a little bit of a problem. So we definitely don't have a side angle pair, which means automatically we have to start with the law of cosines. So let's draw the triangle, label it A, B, C, and we have our opposite side lengths. So side A has a length of 24.6 units. Side B has a length of 16.2 units. And then side C has a length of 33.5 units. So from the very beginning, side B is the smallest side, which means angle B should be the smallest angle. And then side C is the largest side, so angle C should be the largest angle. So we need to use our law of cosines because, again, we don't have an angle, therefore we can't find a side angle pair to start with. Now, which version do we use? Ultimately, it doesn't matter, but again, a good rule of thumb is always start with your smallest angle, because you know your smallest angle is automatically going to be an acute angle. So in this case, our smallest angle would have to be angle B. So I'm going to use the version of the law of cosines that relates directly to angle B. So B squared is equal to A squared plus C squared minus 2AC times the cosine of B. And notice, of course, that I do have A, B, and C. I just don't have angle B. So I'm going to write down my formula. So B squared is equal to A squared plus C squared minus 2 times A times C times the cosine of angle B. So plug in what you know. So we have side B, 16.2. So that's going to be 16.2 squared is equal to A squared, which is going to be 24.6 squared, plus C squared, which is going to be 33.5 squared. And then I'm going to go down to the next line just because I'm about to run out of space. So minus 2 times A times C times cosine of B. And we know cosine of B, B is our unknown. Now, you have to be very, very careful when you simplify this. So on the first example, everything on the right-hand side was all constant. There were no variables. The variable was almost already isolated. So you can just plug all this into the calculator and no problem, take your square root, and then there's your value. We're in a slightly different situation here. So notice our unknown is inside of some other stuff. So it's not by itself. Our unknown is not by itself. What's isolated is not an unknown. It's another constant. So we have to be careful about how we simplify. And there is one very, very common error that most students are going to make at some point, and it's okay. Make it one time and then never make it again, or hopefully don't make it because I'm going to point it out now, and so you'll know to look for it. If you look at the right-hand side, you're going to square this value, you're going to square this value, and then it's tempting to say, okay, I'm going to square these, I'm going to add them together, and then I'm going to subtract 2 times 24.6 times 33.5. I'm going to combine all that together because that's all constant. You cannot do that. Specifically, what you cannot do is combine these two terms with all of this. The reason you can't combine them with all of that is because all of that is then multiplied by the cosine of B. So this term and this term will be considered like terms. They're just constants. You can combine them. But this term, this is one whole term that contains a trig function and a variable as part of it. So you cannot combine those constants with what will be the coefficient for this cosine because those are attached to the cosine. So essentially what's going to need to happen is we're going to need to simplify just a little bit at a time, move some things around, and isolate our cosine of B. But we have to do it very, very carefully. So we're going to show a few more steps here than we would when we're just able to plug it into the calculator directly. So we want to start by squaring everything that needs to be squared. So clear my calculator, 16.2 squared, and do not round. For now, we're not going to round. So 262.44, that's going to be my value on the left-hand side. Okay, 24, oops, can't type, 24.6 squared, 605.16, again, do not round, plus 33.5 squared, so 1,122.25. And then we're going to multiply 2 times 24.6 times 33.5. And again, this part's still unknown, so we just leave it as is. So 2 times 24.6 times 33.5. And that's going to give me, so minus, this is a negative term, minus 1,648.2. And that is multiplied by the cosine of b. Now here is where it gets a little bit more tempting to do what I described that you're not supposed to do. You immediately think, okay, I want to combine these and then I'm going to subtract this. You cannot do that. This and this, those are both like terms. They can be combined, but this whole term has a variable as part of it. So it is not a like term with the other two. It's its own thing. So you can combine these two, and certainly that's what you want to do, and then you'll want to move them to the other side, because the idea is whenever we have a variable, of course, we always want to isolate it if we want to solve for it. So I'm going to combine those and then move them over, or alternatively, we can just take 262.44 and just subtract each of these in one step, and that's probably going to save a little bit of time. So 262.44. Now we're going to subtract 605.16. It's positive, so subtract it, move it over. So minus 605.16. And then we're also going to subtract this, move it over. So minus 1,122.25. Now, are we going to do something with this? This is negative. You want to add it, right? Nope. Because remember, it is multiplied by something. It is part of this whole term. So you can move these two terms over. This stays together as one whole unit. So it's a negative coefficient in front of cosine b. So it just stays where it is for now. So I'm going to hit enter, and that's going to give me what I now have on the left-hand side of my equation. So negative 1,464.97, and that's now equal to my term that was left over. Watch your sign because it is negative. So negative 1,648.2 times the cosine of b. Okay, so we're getting closer. What do we need to do next? Well, we need to get rid of the negative 1,648.2. It's tempting to want to add it, right? You can't add it. It's multiplied by the cosine. In order to get rid of it, you have to divide it out because it is a coefficient. It's a factor for this term. So divide it out from the other side. So I still have the other side in the calculator. I'm going to divide that by negative 1,648.2, and that's now going to give me the value for cosine of b. So once that's divided out, I now have the cosine isolated. So cosine of b is equal to all of that. So 0.8888 plus some. And again, we write down approximations, but we keep the running total in the calculator. Okay, so I recommend at this moment, if you need, pause the video, double check that you can go through all of this algebra and make sure you understand why things are being combined the way they are and why certain things are not combined with other things. That's going to be very important because that's a very easy mistake that a lot of students make. So now the goal is to solve for b. We want to isolate b, which means we need to eliminate the cosine. And just like we use an inverse sine to eliminate sine, we'll use an inverse cosine to eliminate cosine. So that means B is going to be equal to the inverse cosine of my value, so 0.8888, which again is the rounded version of what we have in the calculator. Now, just like with inverse sine, the domain for inverse cosine is -1 to 1. The cosine function takes on values from -1 to 1, so if we're looking for an angle to match with a value, the value has to be somewhere between -1 and 1. So this is within that range of values, so that means we will be able to evaluate this inverse cosine. So I'm going to apply the inverse cosine function to this value, and that's going to give me my angle. So my angle is approximately 27.3 degrees if I round to the nearest 1 decimal. Now you may be asking the question, do we have the same issue here that we had with inverse sine? So we applied the inverse sine and we ran into a situation where we had potentially 2 different answers. Well, that's not going to be a problem here. So if you think about what happens with the cosine function, think about the unit circle. So cosine, we know, represents our x coordinate. And so we found an angle about 27.3 degrees, so something about like that, from our inverse cosine. Well, if we're saying this is the value of cosine, there will also be another angle here on the unit circle that has this as its value for cosine. But if cosine is our x coordinate, we're saying the x coordinate was positive to give us this value for cosine. Well, the only other location on the unit circle where the x coordinates are positive is down in the 4th quadrant. So technically we have an angle down here that also has the same value for cosine. So it would be this angle. Well, automatically you can probably see a problem with that. Whatever that angle is, it's somewhere between 270 degrees and 360 degrees, which means that particular angle cannot exist within any type of triangle, regardless of whether it fits with anything else. It doesn't fit just by itself because everything in a triangle has to add up to 180 degrees. So there's no issue here when we use the inverse cosine with us running into 2 different possible solutions. It just doesn't happen when we use the inverse cosine. So this value for B will be the only value for B. So angle B is going to be the acute angle 27.3 degrees. So now that we have this angle, we now have our side angle pair. And so we found our smallest angle. Now we go to the next smallest angle. So the next smallest angle will be angle A, since it's opposite the next smallest side. Now it's still going to have to be an acute angle because we can only have one obtuse angle, and so it's definitely, if we have one, going to have to be opposite the largest side. So automatically that tells us when we use the law of sines, we should get an acute angle for angle A, and any angle that is not an acute angle cannot represent angle A. So let's set up that relationship using the law of sines, using our new pair. So the sine of 27.3 degrees divided by the opposite side length, 16.2, is equal to the sine of my unknown angle, in this case angle A. So the sine of angle A divided by 24.6. Okay, so now we need to isolate the sine of A. So sine of A is equal to 24.6 times the sine of 27.3 degrees divided by 16.2. So that means angle A is going to be the inverse sine of this value, whatever this value happens to be. Okay, so plug that value into the calculator. and then take its inverse sine. So 24.6 times the sine of 27.3 degrees divided by 16.2. Okay, we get something between -1 and 1, which means when we take the inverse sine, it will be defined. And sure enough, we get an angle of about 44.1 degrees. Okay, so let's put that into the triangle. Now again, it is worth mentioning, what about the other angle? Remember, the other angle we get from inverse sine, the one that's supplementary to the angle we have. So 180 minus 44.1, which would be 135.9 degrees. Well, if you look at the angle we already have, 135.9 would be okay. It would fit with this angle, but it would violate that rule for angles and their opposite sides. So 135.9, that's an obtuse angle. Automatically, that would have to be the largest angle in the triangle. So if we're saying that angle A is the largest angle, it needs to be opposite the largest side, which we know it's not. We know angle C is going to be opposite the largest side. So because this additional angle would violate our rules for the triangle, we know that's not a possible angle, and it's only going to be the acute angle that we found. So again, solving for the smallest angles first is going to help you avoid those situations where it seems like an angle might work, but it really doesn't work. So now that we have those two angles, we use law of cosines and then we use law of sines. Now we can solve for angle C directly. So C is going to be 180 degrees minus the two angles I already know. So 44.1 and 27.3. So 180 minus 44.1 degrees minus 27.3 degrees. So 180 minus 44.1 minus 27.3, and that's going to give us the obtuse angle 108.6 degrees. So angle C has a measure of 108.6 degrees, and sure enough, largest angle opposite the largest side. So this now covers all of our possibilities. So you may be thinking, well, there is one more possibility. What if instead of being given all the sides, I'm given all the angles? Well, unfortunately, being given all the angles is not enough information to find a unique triangle. So, for example, suppose you're told your triangle has 3 60-degree angles, okay? So all we know about a triangle that has 3 60-degree angles is that it's equiangular, or we can also say equilateral, which means all the sides are the same length. But they could all be a length of 1, they could all be a length of 2, they could all be a length of 1 million. Just knowing the angles doesn't actually give us enough to define a unique triangle. So we have to be given at least one side length. So we don't have to be given angle measures as we've seen here. We can solve for all of our angles just being given our sides, but we do need to have at least one side length in order to solve for a unique triangle. So in addition to the strategies we have for solving for unknowns within a right triangle, just setting up those trig ratios, either solving for a side length or solving for an angle, law of sines and law of cosines is going to give us the extra tools we need in order to solve for pretty much any situation, any triangle, regardless. So if we can draw a triangle to represent our situation, either our trig ratios or our law of sines or law of cosines, those are going to allow us to solve for pretty much anything we need within that triangle.